So we'll continue, and what we observed at the end of the last segment is that the only contribution we need to really worry about and expect it to be any different is the new one, right? And so we consider the time-dependent term, right? Right, and the time-dependent term is this one, integral over omega WH, comma, sorry, there is no comma here, that's the whole point, WH rho partial time derivative of u dv. Okay, this is the one we need to consider. Sorry, UH here. Okay, it should be completely straightforward now because we already have our expansions for WH and UH, right? And in fact, let's just make one observation. In order to consider this, what we need to do is use derivative of UH with respect to time. The partial time derivative is, after all, nothing. So, and therefore, furthermore, restricted over a particular element, right? That partial time derivative in an element E is nothing other than sum over A, NA, we know all about those, D A E dot, right, where the dot denotes a time derivative. Okay? Right? Well then, the way this works out then is that integral over omega WH rho multiplying the time derivative is sum over the elements, right? Integral over each element of the following, right? Now let's write out the usual sort of summation that we have. Sum over A, NA, CAE, right? And we know that this first parenthesis is what gives us the WH term multiplied by rho. And for the next term, we have now sum over B, NB, DB, E dot dV. Okay, simple as that. All right, so I'm just going to carry along this sum over E as well, right? Because we know we've done this sort of thing so often in the past that we know how it all works out. Okay, so let's just do that. So this is a sum over E. Right, as before, now I'm going to pull out the sums over A and B. We have here C, A, E, integral over omega E, NA, rho, NB, dV. We have there the integral, and we get here dB E dot. Okay. All right. So, if you stare at what we have here for the integral that I've put in parentheses, it should be clear that for a given element, when you carry out that integral for a combination of basis functions on node A and B, you get a scalar, right, in every case. Okay? this resulting matrix or these resulting terms are going to be of a form that we've not encountered yet before. Okay, we've encountered related, not really related terms, but if you think about the term that gives rise to our conductivity matrix or our diffusivity matrix for this sort of problem, it involves derivatives on the NA and NB, right? It involves spatial derivatives, right? We don't have any of those in this term, right? So this is a different type of term. I am going to denote this integral MAB sub E, okay, right? And this term that I've just written out, MAB sub E, can be further assembled into a matrix vector form, right? And we know how that happens, right? So then from here, if we just use CE equals C1E up to C number of nodes in the element E right, and the same thing for D E. DE we know is just D1E up to D number of nodes in the element sub E, okay? However, we also know that in the particular form that we are dealing with here, we have a DE dot, right? Because we get time derivatives of each one of these terms. I'll make this dot a little bigger than the dots of the ellipses, okay? So, when we get all of that, what we observe is that this integral that we started out with, this mystery new integral, essentially reduces to integral over omega WH rho right. So this integral that we're trying to evaluate is essentially now sum over E CE transpose, right? By assembling all those, by replacing the explicit sum over nodes A and B, right? So replacing that explicit summation which we had on the previous slide here, right? This explicit summation. What we're able to do by defining these element level vectors, we know, is get rid of that explicit summation, right? And we are masters at this as well, okay? What that means is that our MAB scalar terms slot themselves nicely into a matrix, right? They slot themselves into a matrix that I am going to call the M bar AB matrix. Sorry, it's not AB. I've just got rid of the AB. The M bar E matrix, okay? And that is multiplying a D bar dot E vector, okay? You also know why I'm using bars here, right, rather than the final forms, because we know that we can have this issue of Dirichlet conditions there. Okay, so just because after we apply the Dirichlet conditions, the final matrices that we have are going to be reduced in dimensions. Also, the final D vector or the D dot vector that we have is going to be reduced in dimensions through exactly the process we've observed before for handling Dirichlet conditions. Okay, it's in sort of preparation for that, in anticipation for that I'm calling these this matrix M bar and M bar E and that vector D bar E. Okay, that's all. Now, this matrix is what is called often the mass matrix. Okay, in the context of finite element methods, any such matrix that's obtained by directly multiplying the basis functions, no derivatives, right? No spatial derivatives on the basis functions. Directly multiply them and integrate over the domain, maybe multiplying with a row, right? And you've already seen that in some cases the row could be 1, right? So that case is also covered, right? The important thing is that it is when we form a matrix of this type which involves a direct multiplication of the basis functions over an element, right, and their integration, it's called the mass matrix, right? And in this case, of course, the element mass matrix. Okay? All right, it's a new matrix that we've not previously encountered. Okay? Now, I should make a remark here, which is that if we have a general element that is that is not that doesn't have one of its surfaces coinciding with the Dirichlet boundary, then of course we know that the CE vector for that element is going to be full. It's going to have as many entries as the nodes in the element, and likewise the D bar vector, right? For that case, what sort of a matrix is M bar? Okay. So for a general element, omega E, such that the boundary of omega E intersection Dirichlet boundary is the empty set, right? So an element that does not have one of its surfaces coinciding with the Dirichlet boundary. For such an element, we observe that the dimension of CE equals NNE. Okay? Right? Therefore, what that implies is that for such an element, what can you tell me about the M bar matrix? Okay. Recall that the M bar matrix is now going to have this form. M11E up to M1 NNE E, M NNE NNE E, and here we'll have M NNE 1 E. Right? It should be obvious that this is a square matrix with dimension NNE times NNE. What more can we say about it? If I have a general term here that is MAB E, and we have a term here which is the sort of the transposed position in the matrix. What can we say about MAB and MBA? Right? That's right, they're equal. Right? It just follows from the definition of one of those components, right? Each of them is just the integral of NA times NB multiplied by rho integrated, right? So they're symmetric, right? So basically, we have M bar is a symmetric matrix. Okay. All right. One can also show, using the properties of our basis functions, that the M bar matrix is positive definite. Okay. Right, and you recall what that means, right? So if we have some general vector, well, actually, well, it's true for M bar E as well, but yeah, well, it's okay. So M bar E is positive definite. So what we see is that what that means, as you would recall, is that if we took any vector C, right, and we form this product C transpose M bar E, sorry, if you took any CE transpose CE, right? And remember, CE can be arbitrary, right? It could be any vector. This is greater than or equal to 0 for all CE being NNE dimensional vectors, right? And in fact, it's equal to 0 only if C, the CE vector itself, is equal to 0. Okay, this is what we mean by a positive definite matrix, and indeed M bar E is positive definite. Okay. All right, so this is one remark about properties of the matrix. There is another remark which I'm going to make, which is that M bar as computed here is what we call the consistent mass matrix. Okay, okay, one can also do a lumping. Okay, and what a lumping involves is computing a consistent mass matrix and then summing up all the elements along a row and putting that sum on the diagonal. Okay, so it's an approximation. It's not that's why it's not called a consistent matrix, right? So a lumped element mass matrix is the following, right? M E say tilde. Okay, which is obtained as follows. On each diagonal, you sum over sum over B, M, in this case you sum over B, M1, B, E, okay, and put it there and make the others 0. Okay. Likewise, you do that for all the diagonal elements. Okay, and every other element is 0. Okay, right, which basically is telling you that M tilde E AB, right, the AB component of the M tilde matrix is simply sum over B M A B E, right? If A equals B. Well, if this is to be the case, sorry, I need to make a correction here. I need to have a new index for the sum. Okay, so if A equals B, which makes it a diagonal element, then you simply sum up over, you sum up the elements in that row. Okay, and put that sum on the diagonal. Okay, and it is equal to 0 otherwise. Right, it's just a sort of quick and dirty way of diagonalizing the matrix, right? It's not a proper diagonalization through defining orthogonal basis functions or anything like that, right? It's just a way to simply lump it and define a diagonalized matrix. And you also see why it's now called a lumped element mass matrix, right? Because you're lumping all the mass at the nodes. All right.